Hello, we are Rexicoricofallapatorians. My name is Lucas, and we are going to explain topic 12.9, dependent motion analysis of two particles. Basically, we're going to predict the position and velocity of one object that is in direct relationship with another object.
I'm on vitro, and we built this structure to show how the motion of one particle depends on another. And we chose an aluminum sleeve to go on a copper-plated steel rod, which reduces friction. And we connected that with a string over a pulley and connected to another mass. And our calculations are going to show that when this is pulled all the way to the bottom, we can calculate the height that it rises and the velocity of the sleeve with the known velocity of the nut. And here's how it works.
My name is Josh Keener, and I'm going to show you how we prove the math behind the distance that it's going to travel and the velocity. First, we drew our free body diagram and showed where the sleeve ended up and where it began from, as well as the ring that we were dropping. So we knew the value of how far it fell, how high it was initially, the initial distance between here, which is constant, and then we used the pulley equation of L equals SA plus SB. SA is the length here, SB is the length over here. And we calculated the change in those to be 10.625 inches. They equal each other. The amount that's going to change on this side is going to equal the amount it changed over here as well. Once we did that, we moved into up here, where we calculated the final distance from the datum line but off the free body diagram. Then we plugged into this equation or plug that into the equation of delta y equals the y initial minus the y final to give us our change in the distance, which is 13.7 inches. So in order to calculate the velocity, we have to go back to our position equation that we derived earlier. Doing that, we plug in what SB is on the relationship with x and y. Y is going to change, x is never going to change. So in order to do this, we have to take the derivative of that to get the equation in terms of velocity. So we have the velocity equals the derivative, that's the whole derivative of this portion. We use delta y because we're trying to calculate the change in the velocity, which was initially 0, so the change in velocity is also the final velocity. Given that, we can take the velocity of A, which we derived from our testing, and we calculated it to be 7.9 inches per second. When we plug that in, it's in a downward direction, so it's negative. We plug that into the equation along with the other variables we determined earlier and solve for the velocity of B, which is 10.5 inches per second going up.
I'm David Hudlow, and in order to work our calculations, we had to have some known values. So we measured the height that the nut was going to be starting at, and that is what we used here, and we used that to calculate the height that the sleeve was going to go up. And then we also needed to measure the velocity. So to do this, we took the apparatus to the physics lab and used a motion detector to calculate or to give us the velocity on the computer. So we had the motion detector viewing the nut, and we released the sleeve and got the velocity of the nut, and then with that we were able to calculate the velocity of the sleeve. So once we had done all of our calculations, we took the measuring tape again and measured the actual distance that the sleeve traveled, and in the physics lab we put the motion sensor to view the sleeve and measured the actual velocity that the sleeve had as it passed that point. So we have those here, and we compared them to our calculated velocities and distances, and they were fairly close.
Hi, I am John Harper, and I'm going to kind of explain the difference between our calculated values and our actual measured values. To begin with, we took the present error, and the error in our distance between the measured and the calculated was 0.75%, and the error in the velocity was 11.7%. A couple reasons for the error in the velocity were our pulley. It was not ideal. It has friction. It's not fixed. It can move around. The other problem is we didn't have any ideal strength. We had to work with thread. And as you can see, the thread stretches a little bit, which is not always a good thing. In addition, even though we tried to have frictionless surface between our sleeve and our rod, there is actually friction in there that is inhibiting the motion when it falls. Another factor that would explain our errors is every time that this falls, it bounces several inches up, which would interfere with the motion detector correctly assessing the velocity. And for those reasons, that is the difference between our errors and our actual. In conclusion, we have successfully proved that the motion of one particle and its velocity can directly depend on the motion and velocity of another particle. In addition, we have showed that our system is accurate and is able to measure the velocities and positions of one particle and calculate it based on the velocity and position of the other particle. Through our calculations, we have shown the relationship between the two particles, and through testing, we have verified that that relationship is in fact true.